Okay, let's suppose that we wanted to determine if the proportions for the different colors in a large bag of M&Ms matches the proportion that the company claims is in their candies. So I can't remember where you found it. I remember looking this up one time. I just don't remember where you find it. But somewhere Mars has published, or Hershey's, whoever makes M&Ms, can't remember, has published their actual proportions for the M&M colors. So let's say we want to test whether a certain bag of M&Ms matches those proportions. Well, one thing we could do is we could record the color of each candy in the bag. So this would be univariate categorical data. We're only looking at one variable, color, and it's broken into categories. So how many categories for color could there be? Yes?
Okay, I think this would be univariate. Okay.
Sorry about that. I forgot that was a blank. Okay, how many categories for color would there be for M&Ms? 5? Let's see. Let's try to name them based on this picture here. Let's see. We've got orange, brown. Let's see. Yep. And they're also, as Yancy pointed out, they're also right below it, so you can just look at the table. But yeah, there's orange, brown, yellow, blue, red, and green. In a normal bag, you get to your Christmas bags, and then they're all just red and green. And then you get to your 4th of July bags, and they're red, white, and blue. That was, so kind of a side story. My brother, when he got married, since he was in the Marines, they did a patriotic themed wedding. When they were planning for the wedding, I can't tell you how many stores we went to looking for bags of red, white, and blue M&Ms. We had to get both milk chocolate and peanut, and we needed them to make like we essentially mixed them with Chex Mix to have like in the middle of the tables. Of course, this was all before COVID and everything. This was, I guess they've been married 2 years now in February. But yeah, we were going to stores, going to the candy aisle. Oh, no red, white, and blue. Okay, we'll leave now. So, good grief. Anyways, there's 6 colors, so we're going to say K equals 6. Now, what's K? K is just kind of a letter right now that appeared. K is used to denote the number of categories for a categorical variable. So K is the number of categories. So, again, we could count how many candies of each color are in the bag. In this particular bag, we had 23 red, 28 blue, 21 green, and so on. So this is called a one-way frequency table, and it's used to display the observed counts for the K categories. It's one way because there's only one variable. Like I said, Monday and Tuesday we'll look at two-way tables. A goodness to fit test will allow us to determine if these observed counts are consistent with what we expect to have. So let's say we got our proportions from the website. We could test to see if what we have is close enough to what we would expect. So let's talk about some notation. We already said K is the number of categories. P sub 1 is the true proportion for category 1. P sub 2 is the true proportion for category 2. And we just keep going until we get to the last category. P sub K is the true proportion for category K. Since these are proportions, and we've taken into account all the categories, if you add up all proportions, you would get 1. You should get 1. So P sub 1 plus P sub 2 all the way to P sub K would give you 1. So let's talk about our hypotheses. To me, this is one of the easiest pair of hypotheses that we've had. So the null is the hypothesized proportions for each of the P's. P1 equals its hypothesized proportion. P2 is its hypothesized proportion for category 2, etc. The alternative is simply that H naught is not true. That's your alternative. H naught is not true. So if we reject H naught, that means at least one of the true categories differs from the corresponding value. It's not saying every one of them is different. We could only have P2 be different and the rest are the same. What this means is that at least one of the categories is different. Now, we're not going to do this in here, at least not right now, if we do. But one thing you could do is say, okay, I'm going to test, let's say we have 8 categories. I'm going to test it on 8 of them. Oh, I reject. So that means at least one's different. You can then go through the list and say, this one looks like to be the biggest difference. I'm going to throw it out, run the test on the remaining 7. If you do that and then you fail to reject, then you found the one that was different. So you could do that. Like I said, I don't think we're going to do that in here, but that's something that you could certainly do. Because all our hypothesis tells us is that at least one's different. It doesn't tell us which one it is. I feel like that would be a good AP question. Have y'all figure out which one is different. Sounds painful? Okay, let's look at expected counts. Okay, so for each category, the expected count for that category is the product of the total number of observations with the hypothesized proportion for that category. So n times p whatever. N times p1, n times p2, etc. So let's look at a sample of faculty from a large university system. So this news person wants to test to see if each of the groups occurred with an equal frequency. So what are the groups? Well, we have our categories are whether they're a full professor, associate professor, assistant professor, just an instructor, or adjunct or part-time. Those are our categories. So how many total do we have in our sample? Well, there's 5 categories, so K is equal to 5. How many total samples do we have? Like if we add them up, what would our N be? 154, that's right. I'm just going to let this come out. There we go. Okay, now if I add up all my hypothesized proportions, what would I get for that total? 1. You should get 1. If you get something else, that means your proportions are off. Then we have the expected count. So the way you get that is you times the hypothesized proportion by your total up here. So you would say 0.2 times 154. 0.2 times 154. And you would just keep doing that all the way down. So if we did 0.2 times 154, what would we get for our expected count? 30.8. Since they're all 0.2 in this case, every one of them would be 30.8. You add them all up, and you end up with 154 again. Okay, questions on this example? Okay, next. So let's talk about our hypotheses. We've already kind of touched on them, but let's touch on them again. So the hypotheses, we said it's P1 all the way to PK, P sub K, where the hypothesized proportions are for category 1 all the way to category K. The alternative is simply that H naught is not true. So like this is almost as simple as far as writing the hypotheses, but equals and not equals. Now for our test statistic. we have that chi squared is equal to the sum of the observed minus the expected squared over the expected. So we do that for each cell or each category. Observed minus expected squared divided by expected. So if I'm squaring this, will the numerator ever be negative? No. It'll always be positive. What about the denominator? Will the denominator ever be negative? That's exactly right. No. It won't be negative because it's like a count. So for a chi-squared test, this value can never be negative. It will always be positive. So the goodness of fit statistic, which we denote by chi-squared, is a quantitative measure to the extent to which the observed counts differ from those expected when H naught is true. Okay, so p-values. Just like we've done all the way through, we're going to focus on p-values to make our decision. And when H naught is true, and all expected counts are at least 5, then chi-squared has an approximate chi-squared distribution with k minus 1 degrees of freedom. Where's my pen at? So k minus 1 degrees of freedom. Therefore, the p-value associated with the computed test statistic value is the area to the right of chi-squared. Area to the right of chi-squared. We've been dealing with area to the left for like z and t. Now we're going to deal with area to the right of chi-squared under the k minus 1 degree of freedom curve. So I kind of underline the 2 blanks in case you weren't paying attention. So we've got some assumptions to deal with. As always, this time though we only have 2 assumptions. So there were 3, now there's 2. First one, we're going to have it forever. They have to be based on a random sample. Observed cell counts must be based on a random sample. Also, the sample size must be large. And we can say it's large enough as long as every expected cell count is at least 5.
You say you're testing similarly with
You want to get it made 100 argument sample. You get it rounded by saying it's a single cell, one of these, and just do this one. Like instead of it was just one thing. You say the single cell.
So you're saying, like on the previous example, let's say we just looked at adjunct.
Yeah, like you just want to know that you can have a large enough sample for it to be considered large. Otherwise, can you say well, a single cell one of these? Did I work around?
I don't think that would really work, because if you did it that way, what would your hypothesized proportion have to be?
Exactly.
It has to be 1. So, of course, it would make sense, because 100% of your data would be that. So nope, that wouldn't work. That was a good question, though. So let's look at some facts about the chi-squared distribution. First off, different degrees of freedom have different curves. So the one on the screen is the curve with 3 degrees of freedom. I don't want to reveal that answer yet. So what do you notice about this curve? Like, how would you describe its shape? Positively skewed. What's another way to say that? Skewed to the right. That's right. So chi-squared curves are skewed right. Chi-squared curves are skewed right. However, watch what happens as degrees of freedom increases. So we were at 3, then we got a 5, then 10. What's happening to it? It's becoming less and less steep. So as the degrees of freedom increases, the chi-squared curve starts shifting towards the right and becomes more and more like a normal curve. Okay, so we can kind of see that happening because this very tip-top curve, I know y'all's notes aren't printed in color, so it doesn't have quite the same impact as it does up on the screen. But this very top one is where degrees of freedom are equal to 1. This one down here is where degrees of freedom equals 15. So look how drastic the change is, going from 1 degree of freedom all the way down to 15 degrees of freedom. Okay, I don't like this table. It's totally different than the one y'all are going to be looking at on your formula chart. So let's look at our formula chart. It's table C. I think they said last period, the second to last page in your formula chart. Okay, so on this one, you'll find your degree. When I explain this, it'll be kind of complicated, but then when we work an example, it will make sense. So you'll get when you're working these problems, you'll get your test statistic. Let's say it's 8.2. You get 8.2, okay. So let's say your test statistic is 8.2, and you have 6 degrees of freedom. The way this would work to get, and this table won't give you the exact p-value. That's why I do not like it. I like exact things, and this is not exact. But let's say you have 6 degrees of freedom. Your p-value, not your p-value, your test statistic is 8.2. You'll look through this row to find where will 8.2 fit in. So if our value was actually 8.2, it would fit in between these two columns. So that means your p-value is going to be between 0.2 and 0.25. Not very precise, is it? No. So let's look at how you can get a more precise one on the calculator. So if you remember back to when we were doing the t-test and we were having to get p-value, what did we hit? We did second, and then it's the same problem. If you used it for a t-test, I think that in that same menu where you pick t-CDF, you look further down and it'll say chi-squared CDF. Yep. So on the 84s, you'll do second and vars. And then option 8 is the chi-squared CDF. So second vars. Option 8 is your chi-squared CDF. On the inspires, all I can say is go to the same place you did TCDF at. If you know how to do that. And it'll be close to that same area. So I'm going to go there just so we can see what it looks like. It's similar. You picture your lower bound will be your test statistic. So maybe you want to make note of that somewhere. When you're doing it in your calculator, your lower bound is your test statistic. Your upper bound is just a really big number. 9999 or whatever you want it to be. Maybe you put your birthday in there with no dashes. Today's date, 12/11/2020. No dashes, whatever. Really big number. Put your degrees of freedom, and then you'd paste it and hit enter, and that would give you the p-value. Okay, back to the PowerPoint. So let's look at an example. We have 2 examples to do. Here's the first one is using that professor data that we worked with already once. So we're going to let P1 be the proportion of full professors. P2 is the proportion of associate professors. P3, the proportion of assistant professors, and so on. So let's try to come up with our hypotheses. The hypotheses, remember, are that each of the p's are equal to the predicted value. not predicted, but the hypothesized. So P1 for full professors. What did our table say that we did earlier for the hypothesized proportion of full professors? What did we go back to our table. Actually, I'm going to go forward a little bit. Nope, wrong way. Our hypothesized proportion was 0.2. On all of these, they were 0.2. So for our wrong way. So for our null hypothesis, we would say P1 is equal to 0.2. P2 is equal to 0.2. P3 equal to 0.2. We just have to go through and list them all. P4, 0.2. P5, 0.2. That's our null hypothesis. The alternative is simply that H naught is not true. So those are our hypotheses for this test. Okay, so we need to look at assumptions. Now they give us this nice big paragraph. I'm not going to make it a really nice big paragraph, unless you want to. We need to check two things. First, we want to make sure that they're all the expected counts are greater than 5. So I'm just going to say counts greater than 5, question mark. That's where we have to go and look at our table. So what did we say we wanted all the expected counts to be when we did this? 30.8. So we could say something like all expected counts are 30.8, which is greater than 5. Done.
There were different counts to get the list them all, or can you just say all expected counts are greater?
If your table is there in the problem already, you could say they're all greater than 5. If you're, like one thing I saw, and I've returned y'all's homework from chapter 5, but some of y'all just, the question in the book says, is this line a good fit? And y'all just say, yes. And so I'm reading your solution, and all your solution says is yes. Guess what? What's this random yes mean? So if you draw the table, then you can say yes, all per the table, all expected counts are greater than 5. If you don't, then I need you to listen up. Does that make sense? Okay, and then number 2, we have to check to see if it's random. Now, in this problem, we don't know for sure how they obtain the sample. So for the purposes of this example, we're going to assume that it's a random sample. There's not really a short way I can put that other than just what's already here. I don't know how you can really shorten that too much. So just, you can paraphrase it, do whatever you want, but I guess in summary we can say, let's assume so for the sake of this problem. Okay, let's start calculating. I don't want it to show the calculation. I don't think it cares what I want. There we go. That's what I want. Okay, so now we've verified the assumptions. Now it's time to do the grunt work. You've got to actually calculate this test statistic. So as I've said in the past, first step, write down your formula. So chi-squared equals the sum. Now you don't have to write, if you don't want to write this whole big thing, I'm not worried about you saying cell count. You can, if you want to be just like, that's what the book says, that's what I'm saying, that's what I'm putting. Just, you can say observed minus expected squared divided by expected. So that's what we have to do for each one of these. And we're going to say chi-squared equals, and then go through and do that for each one of these 5 categories. The first category, observed. Well, there were 22. Minus expected is 30.8 squared. Over the expected, 30.8. Plus. Then we get to the next category. 31 minus 30.8 squared over 30.8. And we keep going through all 5 categories. And if you're wondering, can we do it like this on the homework, where we put ... instead of listing all of them out? Yes. Do the first 2 plus ... plus the last one. That's a valid mathematical way to do it, where you don't have to list everything out. Okay, so I want y'all to claim one of the categories as your own and calculate that value. That way we're not all calculating every value. So why don't we do this? Will, why don't you do full professor? Yancy, associate. Nate, assistant. Let's see. David or Mia, I would like y'all to do instructor. And then Olivia or Taha, I would like y'all to calculate the value for adjunct. And let's do it to 4 decimal places. Okay, so go back. Okay, so Will, did you get yours for the full professor? What did you get?
I got 2.5142.
2 point.
Actually, 2.5143.
Good. Okay. Nancy? Nate? 1.0922. Okay, let's see. Who did I say? David or Mia?
I'm still calculating.
Okay,
I think Mia's Wi-Fi is messing up.
gotcha. And then Olivia or Taha, if y'all have y'alls, you can go and then share y'alls.
I've got mine if they're not ready.
Okay, what did you get?
I got 0.5727.
That's right. And then Olivia or Taha, if y'all don't want to say it out loud, you can put it in chat. If someone want to help them out, what we get? What can we get for this last one? $3.3779. Okay, so if we add all of those up, we would get that chi-squared equals 7.5584. That's right. So that's our test statistic. So now, how many degrees of freedom did we have? Because our next step is to move on to p-value. So we had 4 degrees of freedom. So if we look at our table and look at our formula chart at 4 degrees of freedom, we need to try to find, if we didn't have our calculator with us, try to find where this p-value, or this critical value, I should say, would land. So 4 degrees of freedom. We're looking for where 7 point, yeah. So 4 degrees of freedom, 7.55, it's kind of in between those two values. So between 0.10 and 0.15. Again, not very precise. As a math person, I like to be precise. So we can now turn to our calculator. Now that we know the range, let's just get the exact answer. So go to our calculator. Like I said, the lower will always be your test statistic. So 7 point, what did we say, 5584. Upper is just a really big number. And we have 4 degrees of freedom. So lower, upper degrees of freedom. So our exact p-value is 0.1092. I'll say exact, that's rounded, but to 4 decimal places, 0.1092. Now we have an actual value and not a range. Okay, let's see what they did here. So even here, they said it's between 0.1 and 0.15. Yeah, no, it is 0.1092. So you could be like, well, actually. I'm not trying to do a range here. I want the exact p-value. So however you want to put the process that we just did in your notes, go for it. When you're doing your assignment, I'd like you to tell me the degrees of freedom. And I kind of like how I use the same process we did. So tell me the degrees of freedom. Show me that you looked it up in the table and found what values it was between. And then name the exact using your calculator. So those 3 steps. Degrees of freedom, the range, and then the exact. Now, on this one, this problem, they said that alpha was 0.05. They gave that to us in the problem itself. It says significance level of 0.05, so that's our alpha. Based on that alpha, what do you think our conclusion should be? Should we reject or fail to reject? We fail to reject, that's right. So since the p-value is greater than the alpha, H0 cannot be rejected. Which means there's insufficient evidence to refute the claim that the proportion of faculty in each of the different categories is the same. Okay, questions on this example? Yep. Yeah. Good luck tonight. Kick and block good. Yeah, I heard your name called out last week too on the broadcast. Yep. They were saying that you, on one of the plays, you, as they put, sniffed out the blitz and jumped from your block to catch whoever was blitzing.
Y'all have a good one.
You still writing well, or you good?
Okay, no.
You good? Okay. Next example. So a common urban legend is that more babies than expected are born during certain phases of the lunar cycle, especially near the full moon. So if you've ever known anyone that's expecting and it comes time for a full moon, my God, better watch it. It's full moon. Baby may come tonight. Same thing with like animals and stuff. If you've had animals and you're waiting for them to have their baby, you may watch them a little bit more closely on a night that's a full moon. So the purpose of this example is to see, is there any truth to that, or is it just urban legend? So the table below shows the number of days in 8 lunar phases and the number of births in each phase for 24 lunar cycles, which is almost 2 years. A lunar cycle is about a month. So, well, I was going to ask how many phases there were, but I kind of just gave that away. There's 8 phases, which means our K is equal to 8. K is equal to 8. So we're going going to let each of the proportions pertain to a phase. So P1 is the new moon, P2 waxing crescent, P3 first quarter, etc. All the way to P8, which is the waning crescent. So in this sample, there's a total of 699 days in the 24 lunar cycles that they sampled. If there's no relationship between the number of births in the lunar phase, then we would expect the proportions to equal the number of days in each phase out of the total number of days. So the expected proportions would be the number of days in the phase divided by the total number. So let's see, for P1, how many days were in the phase for P1, which is the new moon? According to our table, there were 24 days that were the new moon. So our P1 would be 24 out of 699, the total number of days. P2, well, let's see. We have how many for the waxing crescent? 152 out of 699. You know, you may be wondering why I'm not turning these into decimals. I'll explain why here in a second. Because when I click to the next piece, it's going to show them all as decimals. But when we get to that big table down at the bottom, I'll explain why. So P3, we would have, again, 24 over 699. And we would just keep going. And then P5, or not P5, P8. P8 would be 152 out of 699. Okay, so they, like I said, they gave us the proportions all to 4 decimal places. And this would be our alternative, this would be our null hypothesis. So these 8 right here are the null hypothesis, H naught. P1 is this proportion, P2, P3, and so on. What did I say our alternative is when we're doing these tests? H naught is not true. So there's our hypotheses for this. I'll give y'all a second to get the hypotheses written down. Okay, so we set our hypotheses. Now there were a total in this process. There were a total of 222,784 births in the sample. So if there's no relationship between the number of births and the lunar phase, then the expected counts for the category would equal n, a hypothesized proportion. So let's calculate the expected number of births for each category. So here's why I didn't really want us to put all these in decimal form. The reason is that if you notice, let me first write down my whole n. It's 222,784. If you notice, our n is the 100,000ths place. Our 100,000, I should say, place. 200,000. Our decimals, though, yes, we go to 4 decimal places, but this is the 10,000ths place. So if we use these decimals to calculate the expected number, we're going to be off. Like that, when I did it this morning, my first value was off by like 8 births. So yeah, no, we're not doing that. So, anyways, let's do 222,784 times. What did we say P1 was? What was the fraction for P1? 24 over 699. And that would equal should be 7,649.24. And then we would go through with the next one. So 222,784 times, what was our P2? 152 over 699. And what would that one give us? $38,445. Let's do 2 decimal places, so 0.16. And then you would keep going in this manner. For the sake of time, I'll just kind of give the rest to y'all. But you would keep going in this manner, getting these values. Yes. 'Okay, so once we have all of our values, then it's time to compute the test statistic. Now, last period I had us actually actively compute it and go through each step. We don't have that much time left. I mean, yes, we're almost done, but I don't want to bore y'all any more than what I already have with the just brute force calculations. So remember that for the test statistic, it's observed minus expected squared divided by expected. That's what each one of these here is. Observed minus expected divided by expected. If you were to calculate all of these out and do it correctly, your chi-squared would be 6.311. That would be your test statistic. 6.311. Okay. So now if we look at our table, we have 7 degrees of freedom because there's 8 categories. So 8 minus 1 gives you 7. They don't give us an alpha. So we're just going to say alpha is 0.05. If we looked at our table, we would see that our test statistic doesn't even register under 7 degrees of freedom. The smallest value it has is 9.04, which means our p-value is greater than 0.25. Now, if we were to use the calculator, if you use the calculator, I'll give y'all a chance to do it and share with us what you get. So this is as good as you can get on the table. So with calculator, did you get the p-value, Yancey?
Yeah, I got 0.5039.
0.5039. So yeah, if alpha is 0.05, the p-value is sitting at 0.5, pretty much. What would our decision be? Definitely. So since p-value is greater than alpha, we fail to reject H0. So there is not sufficient evidence to conclude that lunar phases and the number of births are related. And we haven't talked about this in a while, which is why I want to ask it. Since we fail to reject, what kind of error could we have made with this decision? Type 1 or type 2? me erase this, and then we can. It says type 2. So you can't really see it, but it is type 2. I just need to erase all this. So we could have made a type 2 error by failing to reject. Not saying that we did, but we should have. So just to kind of review that. Okay, so we are done.